Yes, okay. We are recording now. Yes, we are. Yes, I'm going to share my videos and my lecture notes, but I'm hoping that you are going to use them when you're studying. You know, after the lecture, you need to study on your own, and if some point is not clear or you missed something I said during the lecture, so I'm hoping that you're going to use the lecture notes and the videos for those purposes. But you need to come to the lecture and listen to me and ask your questions. That's the next important thing. After the lecture, you need to study yourself so that you see the points where you are not comfortable with, so you can ask me the next time. Or I'm going to, every instructor is going to set up an office hour, not this week, probably starting with next week. And the schedule, again, is going to be shared with you on the webpage and in office class. Okay? So during the office hour, you can go to the instructor's office hour and ask the questions, or you can just go and listen to anybody else who has come to the office hour, because the office hours are also going to be online. And if anything else comes to my mind, I will share with you. Also, in the syllabus, you will see the list of suggested problems. After the lecture, you need to go, and I don't think there are any suggested problems from the preliminary chapter, but you can try the exercises in the book yourself. Okay, so after the lecture, you should work on your own, try to suggest the problems, but don't keep yourself confined to the list of suggested problems or to this book. You can look at other books, you can try other resources, but again, as I said on the video, if you're going to use internet resources, be careful. Make sure that what you hear, what you read is in accordance with what we are teaching here. So the lectures are the key. Okay, lectures are your, how shall I say, your pointers. Okay, so if you use any other internet resource, please make sure that everything is in synchronization. And if you have any questions about it, again, you can ask. Okay, so in calculus, we work with numbers. Real numbers. And the set of real numbers, we denote it with this funny R. Okay, this is the set of real numbers. And of course, before real numbers, if we, maybe we should talk about the number sets. First, we have natural numbers. We denote it by n. It is a convention, of course. 0 may or may not belong to the set of natural numbers. In this book, it adopts the convention that 0 is not here. Okay, we start with 1. So with numbers, of course, we want to perform operations. The first one is addition. All right. We can add two natural numbers and get another natural number, but in order to have the what we call the unit element for addition, we need to add 0. And when you add 0, then we need additive inverses for a number. We need the number so that when you add them up, you get 0. So natural numbers, of course, in this way is not enough. There are no additive inverses. So we get the set of integers. We denote it by Z. So integers, it includes 0 and each natural number together with the additive inverse. It's negative. Okay, and then on integers, we can define multiplication of numbers. You multiply two integers, you get another integer. And for multiplication, we have the unit element 1. When you multiply an integer with 1, the integer doesn't change. And then this brings up the question of multiplicative inverse. For an integer, can we find another integer so that when we multiply them, we get 1? Of course, for integers, this is not possible. So in order to get additive inverses, we need rational numbers. We denote it by Q. So the set of natural numbers are the set of fractions of the form m over n, such that the numbers m and n are integers, but the number in the denominator cannot be 0. So this gives us the set of rational numbers. Then in the set of rational numbers, we have multiplicative inverses. When you multiply a rational number m over n with another rational number, say p over q, you just, no, okay. When you multiply m over n, let's say, of course, in order to have a rational number, n is not 0, but in order to have the multiplicative inverse, the number should be different from 0, so the numerator is also different from 0. In this case, when you multiply the rational number m over n with n over m, you get 1. So we have multiplicative inverses also. But then rational numbers also not enough. Why it is not enough? First of all, it is not enough to, okay, if you consider numbers corresponding to at least positive numbers, let's say, corresponding to some certain quantity in nature, some length, let's say, rational numbers are not enough to denote all the possible quantities found in nature, like square root of 2. If you construct a right triangle where the two legs have length 1, then the hypotenuse must be a number whose square is equal to 2. And we denote this number by square root of 2. And square root of 2 is not a rational number. Not all numbers are rational. So we get real numbers. How we get real numbers, you know, that's not a simple thing. It's not the construction of real numbers is not something I can talk about here. So we are not going to go over the construction of real numbers. We are going to accept that real numbers are there, and we are just going to use them. Okay. So, but the thing is, the important thing is, real numbers. Oh, my line is not very straight, but suppose this is a straight line. So this is the number line. So real numbers fill out the number line. Okay, so every point on the number line corresponds to a real number, And we usually locate 0. 0 is our reference point. And positive numbers to the right, negative numbers to the left. And the arrow indicates the orientation. Or if you want direction, in which numbers increase. So on the number line, as you go from left to right, the numbers increase. So say if 1 is here, then 2 is here, and here is -1 and -2, and so on. Okay, so this arrow, we don't use arrow at both ends. Okay, on the number line, we use arrow only at one end, and that arrow indicates the direction where the numbers increase. Okay. So on real numbers, we have addition, multiplication, and we have order, increasing order. So we can, given two real numbers, we can say 1 is, so in the real numbers, in the number line, if you have a real number here, A and B, this means A is less than B. Or we can also use less than or equal to, or greater than or equal to, or greater than. So we have order in real numbers. Okay. This order is important. We are going to work with inequalities frequently in this course, so maybe I should repeat the rule for inequality. Okay, so for all real numbers, A, B, C. Is it when I turn my head to right? Is it better now? Okay, good. So for all the real numbers, A, B, and C, okay, rules. If I roll down very quickly, if you miss something, please tell me. So the first rule, if the number A is less than B, then A plus C is also less than B plus C, and also A minus C is also less than B minus C. So if you have an inequality, you can add or subtract a real number, the same real number, from both sides of your inequality. But with multiplication, we need to be careful. Again, if A is less than B and C is a positive number, greater than 0, then A times C is also less than B times C. So you can multiply both sides of your inequality with a positive number. But if you multiply it with a negative number, if A is less than B and C is less than 0, then your inequality is going to change direction. Then A times C is going to be greater than B times C. Okay, so when you multiply with a negative number, the inequality changes direction. Okay. Now, if you have a positive number, then its multiplicative inverse, 1 over A, is also positive. Okay, so 1 over A is the multiplicative inverse. Or sometimes we call it reciprocal of A. So reciprocal means 1 over A. And of course, if your number is negative, then its multiplicative inverse is also negative. And of course, 0 does not have multiplicative inverse. One over 0 is not defined. Does not have multiplicative inverse. 1 over 0 is not defined. We don't write it. It's not correct to write 1 over 0. Okay, there is no such number. 1 over 0 is not a number. All right, so if you have an order between two numbers, between two positive numbers, so if A is less than B and they are both positive, then when you take their multiplicative inverses, the inequality changes direction. They are still positive, the multiplicative inverses, but now in 1 over B is less than 1 over A. If A is less than B, when you take 1 over, when you take the reciprocal, the inequality changes direction only when both numbers are positive or negative, of course. If A is less than B and they are both negative, then again, 1 over A is greater than 1 over B and they are still negative. I'm sorry, I need to write it this way. Of course, if one of them is positive, the other is negative, then when you take the reciprocals, it will stay that way. The negative number is always less than a positive number. So if the smaller one is negative and the larger one is positive, then when you take the reciprocal, the order of the inequality does not change. So when you're going to take the reciprocal of an inequality, you need to be careful whether both numbers are positive or both numbers are negative. Okay. And as I said, the real numbers fill out the number line. That property we call being complete. So I'm just going to write it down. R is complete. Of course, being complete has a mathematical definition, but it is not an easy definition. I'm not going to repeat it here. If you read the book, there is some explanation in the book. You can read it and ask me questions if you have any questions. Okay, but just know that it is complete. So you can think of it as R fills out the number. Rational numbers doesn't fill out the number. Okay. What does it mean? So you can consider, okay, consider the irrational number square root of 2. Square root of 2 has a certain decimal expansion, right? It is 1 point something. And you can evaluate the digits after the decimal point, 1 point. You can evaluate the digits of the number square root of 2. So if you take the first digit, is it 1.2 something? So if you take the first digit, 1.2, it's a rational number. Then take the next digit, 1.21 probably. It's again a rational number. So you keep taking digits, you will keep getting different rational numbers in the number line. But your real square root of 2 is going to be greater than all of those. These are all approximations if you take certain digits, but not the rest. These are all approximations to square root of 2. So in order to get to square root of 2, you need to take infinitely many decimal points. Not possible, right? So on the number line, you can say this is square root of 2. Okay? It's a point on the number line, but it is not a rational number. So if you only consider rational numbers, with the point which corresponds to square root of 2 is going to be empty. Okay? If you only consider rational numbers. So in order to get the whole number line, we have to consider real numbers. And in a way, again, this needs mathematical definition, which we are not going to do here, but in a certain way, the irrational numbers is bigger than rational numbers. Okay? There are lots more irrational numbers because rational numbers, okay, this is beyond this course, but just to give you an idea, rational numbers is the set of rational numbers is what we call in mathematics countable. But real numbers is not countable. So the set of irrational numbers is not countable. Okay. Question? So numbers which are not rational, irrational numbers is a much bigger set. Okay. All right. Now, any questions? Okay. Now, interval notation. This is going to be, where is my page? Where is my page? Yeah, yeah. Okay. Interval notation. This is also going to be important. So I'm going to the next page. Yes. So interval notation. Now, an interval means, first of all, interval must have at least 2 points, and whenever it has 2 points, it has to contain all the points in between. Okay? So there are no gaps no holes in an interval. But what we call endpoints, A and B, it may not include the endpoint. It may be an open interval. So for real numbers, A less than B, the open interval say AB is the set of real numbers which are between A and B. All the real numbers which are between A and B. Of course, you can also consider the closed interval. So, okay, how we denote open intervals on the number line? We take a hole at A and a hole at B and take the open interval and everything in between. You can also consider the closed interval AB, then we denote it this way, is the set of all real numbers which are between A and B, including A and B. Then on R, again, we take A as tilt point, not the whole, and everything in between. Of course, you may have a half open interval. Say open at A, closed at B. This is the set of all real numbers which are between A and B, including the point B, but not A. So A is empty, B and everything in between. Also, you can have the half open interval, open at B and closed at A. This is the set of all real numbers which are between A and B and the point A, but not B. So A is included, but B is not. These are finite intervals, okay? We also have infinite intervals. So you may consider the open interval from the real number A to infinity. This means all real numbers which are greater than A, but without any bound. So we start at A itself is not included, but we take everything greater than A. So there is no end. Infinity here, it's a symbol. It is not a number. Infinity is not a number. It is a symbol which indicates that numbers increase without bound. So all the numbers greater than A, you keep going, you keep increasing your numbers. There is no bound. They keep increasing, okay? So infinity is just it is a notation in mathematics. It's not a number. So you cannot perform operations with infinity. All right. Similarly, you can take the closed interval. A infinity, all the real numbers greater than or equal to A, or from minus infinity to A, all real numbers which are less than A, and the closed interval less than or equal to A. Question? I hope that you're hearing me okay. Do you have any problems understanding what I'm saying? Okay, good. Okay, so maybe let's do some examples on how the intervals come up. So examples, solve the inequalities and no. Is it because of the echo? Emil?
Yes.
Yes. Low. I don't know what, at least right now, I don't know what to do. I will try to, you know, try to learn if I can maybe change the microphone setup or whatever, but at the moment I can't do anything. I'm sorry. For next time I will try. But you can maybe try headphones or maybe I can try headphones. Maybe that will be better. Okay, next time I will try headphones. It is understandable, yes, okay, that's the important thing, but of course it should be better, my voice. Okay, I will work on it. Okay, solving inequalities and okay, all right, I will do that next time. And express your answer in terms of intervals. So these are basic examples just to show you how it works. Maybe, you know, but we need to start somewhere, right? Let's say you have inequality 3x plus 5 is less than or equal to 8. Of course, what we do is take 5 to the other side. We can add or subtract any real number from both sides of the inequality. So you have 3x less than or equal to 3, and then we multiply both sides by 1/3. And 1/3 is a positive number, so when I multiply both sides of the inequality with 1/3, the inequality remains the same, so I get x less than or equal to 1. So in interval notation, it is the closed interval from -infinity to 1. Let's say we have the inequality. Now to work out this inequality, I cannot multiply by x because x is the unknown here, so I don't know whether it is positive or negative. In order to multiply both sides of the inequality with a number, you need to know whether the number is positive or negative. So instead, I take this 2 to the other side as -2 and get 0 on one side of the inequality. And I perform this operation, I get the common denominator, so I multiply 2 with x, and x minus 2x, so I get 1 minus x over x is greater than or equal to 0. So we need to figure out the set of values of x for which this fraction is positive or 0. So we do this by means of a sign table. So first we find when the numerator and denominator is 0. So when 1 minus x is equal to 0, it means this means x is equal to 1. And denominator x is equal to 0 means x is 0. So we are going to make a sign table. For x values, I'm going to use 0 and 1. And I'm going to look at the sign of the numerator and the denominator. And using these, I'm going to look at the sign of the fraction. Now, when x is 0, but the fraction is undefined. I'm going to use double bars to indicate that this expression is not defined. Now, when x is 1, 1 minus x is 0, and it means the fraction is 0. When the numerator is 0, the fraction is 0. Okay, so for each, now I have 3 intervals. For each interval, I'm going to figure out whether 1 minus x and x are positive or negative, and I do this by means of a test value. For x less than 0, let's say we use x equals -1. For x between 0 and 1, let's say we use x equals 1/2. And for x greater than 1, let's say we use x equals 2. When x is -1, you see that 1 minus x is positive and x is negative. When x is 1/2, 1 minus x is positive, x is positive. And when x is 2, 1 minus x is negative, and x is positive. So when 1 minus x is positive and x is negative, the fraction is negative. When 1 minus x and x are both positive, the fraction is positive. When 1 minus x is negative and x is positive, the fraction is negative. So we are looking for numbers for which the fraction is greater than or equal to 0. So we need to take this interval. But we cannot include the value 0 because at 0, the fraction is undefined. But we can include 1 because when x is 1, the fraction is 0. So the solution is the interval, half of an interval, 0, 1. These examples are basically to set up the notation, what we are going to do later, okay? Because we are going to use those sign tables later, okay? And I'm going to use them in exactly this way. Any questions here in this for this example? My third example is again simple, but again, I'm just going to do the example to set up the notation, how we are going to work out, because in the exams, you need to give your complete solution. You need to write down your solution, so it must be understandable. So we need to agree on certain things, how to denote certain things, how to write out certain things, so that when you write your solution in your exam paper, we can understand your solution. So I'm going to work this out the same way. I'm going to take -1 to the other side as +1. So on this side, we get 0. So we are looking for values of x for which the expression 6x squared minus 5x plus 1 is less than or equal to 0. So first we need to, we can try to factor it out into linear terms if possible. Let's see, 6x squared, so we can factor it out as 2x, 3x, and 2 plus 3 is 5. So probably if I take this, right? 6x squared minus 5x plus 1. So if 2x minus 1 is 0, it means x is equal to 1/2. If 3x minus 1 is 0, that means x equals 1/3. So in my sign table, I use 1/3 and 1/2. So 2x minus 1, 3x minus 1, and the product. So at 1/3, 3x minus 1 is 0, so the whole thing is 0. At 1/2, 2x minus 1 is 0, so the whole thing is 0. So for each interval, again, I choose a test value. For values less than 1/3, we can choose 0. Values between 1/3 and 1/2, we can 1 bölü işte 1 bölü 2 arasında bir sayı. 1 bölü 2,5. 5 bölü 12. Güzel. Orta nokta değil mi? Yes, we can take x equals 5 over 12. And for x greater than 1/2, we can choose x equals 1. Okay, at x equals 0, 2x minus 1 is negative, and 3x minus 1 is also negative. When x equals 5 over 12, 2x minus 1, 5 over 6 minus 1, negative, 3x minus 1, 5 over 4 minus 1, positive. When x equals 1, both of them are positive. So for x less than 1/3, the product is positive. For x between 1/3 and 1/2, the product is negative. And when x is greater than 1/2, the product is positive. So I'm looking for values of x for which this whole thing is less than or equal to 0. So I need to take the values of x between 1/3 and 1/2. Oh, I'm sorry. So my solution is the closed finite interval from 1/3 to 1/2. Any questions? Okay, we have another important notion. Absolute value. Now, the definition of the absolute value for a real number x, for a real number, let's say x, the absolute value of x denoted by x between bars is the distance on the number line between x and 0. So on the number line, you put 0, you put your number x, and you look at the distance from 0 to x. Of course, if your number is positive, then this distance is equal to the number itself. But if your number is negative, this is not x, it is. This is number one. If your number is negative, then let's say -1, then the distance cannot be a negative number, right? So if let's say your number is -1, it means to locate your number on the number line from 0, we take 1 unit to the left. So we take absolute value, the distance is not the number x, but its additive inverse, -x. And of course, absolute value of 0 is 0. The distance between 0 and itself is 0. So we can write the absolute value in this way. You can include 0 in either interval, x positive or x negative. So absolute value of x is x itself if x is greater than or equal to 0, and it is -x if x is less than 0. So example, absolute value of 3 is 3, but absolute value of -√2 is -√2, so it is √2. Now, properties of absolute value. The first, maybe very simple but very useful property, that every real number is less than or equal to its absolute value. Of course, for all real numbers. Absolute value of the number and absolute value of its additive inverse are the same. So on the number line, if your number is here, its additive inverse, this is 0. Its additive inverse, you take the same distance, but in the other direction. So you get minus x. But these distances are both absolute value. They are the same. Now, the third one, wait, no, third one, yes, okay. So absolute value, if you take the absolute value of the product of two numbers, x and y, it is equal to absolute value of x and absolute value of y. And similarly, absolute value of the fraction x over y is absolute value of x over absolute value of y, but of course, in this case, the number y cannot be 0. You can see this because if both numbers are negative, then their product is positive. And if one of the numbers is negative, then the product is negative. So by considering the different possibilities, you can see how this works out. But maybe more interesting one is what we call the triangle inequality. Absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. The equality occurs when both numbers are positive or when both numbers are negative. But if one of them is positive, the other is negative, the other side, the right side, is going to be strictly larger than the left side. And same thing with the difference, x minus y is also less than or equal to, because absolute value of minus y is the same as absolute value of y. Now, to see why this is true, we can work it out. So it's your first proof of this course, the proof of the triangle inequality. Very simple one, but it is the proof. So first of all, if you take x plus y squared, it is a positive number, so it is going to be x plus y squared. This is because x plus y squared is greater than or equal to 0. You're squaring, so you always get a positive number. But what is x plus y squared? Write it out. It is x squared plus 2xy plus y squared. But x squared is the same as absolute value of x squared. And y squared is the same as absolute value of y squared. Because they are positive. Now, if I'm going to take the absolute value of the middle term, remember the first property, any number is less than or equal to its absolute value. So if I replace the middle term by the absolute value, I get something bigger, or maybe equal, but it may be bigger. And now this is equal to by property 3, absolute value of 2, which is 2, absolute value of x, absolute value of y, plus absolute value of y squared, which is absolute value of x plus absolute value of y squared. And now I take the square root of both sides. That brings me, okay, this is another important thing. So maybe I should add it as property 0. Absolute square root of x squared is equal to absolute value of x. This is an important property. We are going to use it again later. Absolute value of x squared is square root of x squared is absolute value of x, not x. Okay, because maybe x is negative. You need to take the absolute value. Okay, so back to our proof. I take square root of absolute value of x plus y squared less than or equal to square root of absolute value of x plus absolute value of y squared. This is absolute value of x plus y, absolute value of x plus absolute value of y. But of course, since the numbers are positive, absolute value of x plus y is always positive. The property -1. I'm sorry, we didn't say this either. Where's my page? Where's my page? My page. Oops. Okay, property -1. Okay, not the example. Property -1. Absolute value of x is greater than or equal to 0. Oh, it's the distance. I don't need to say it as property, but maybe we should. Okay, so since it's positive, the absolute value is equal to the number itself. Similarly, absolute value of x is positive, absolute value of y is positive, so the absolute value of the sum is the same. So end of the proof. And for the other one, absolute value of x minus y, we just write it x plus f minus y less than or equal to absolute x plus absolute minus y, but absolute minus y is the same as absolute. But now I have another one, and I'm going to write it and finish for today. Property number, what's my property number? 5. Absolute value of x minus y, yes, it is less than or equal to absolute x plus absolute y, but it is greater than or equal to absolute value of x minus absolute value of y. And the proof is similar, just for the proof. Consider absolute value of x minus y squared. And proceed as we did above, you're going to get this equal. Okay, any questions? Yes, I'm going to share my lecture notes, and I'm recording to the cloud, so as soon as I have the link, I'm going to share the link for the video with you in OttiClass. You know how to use OttiClass, right? I will share the link for the video and my lecture notes in OttiClass. Okay, so that's all for today. Let me stop the recording.